Welcome to the first afternoon session. We're going to start with a talk on exploiting fully observable and deterministic structures in goal POMDPs by Håkan Warnquist, Jonas Kvarnström, and Patrick Doherty, and the talk is going to be given by Håkan.
Yes, hello. So as Andrew said, my name is Håkan Warnquist, and I'm an industrial PhD student, so I also work for the Swedish truck manufacturer Scania. And we're here to present a paper exploiting fully observable and deterministic structures in goal POMDPs. So I will begin by presenting a motivating example of a situation where we want to apply the techniques that are presented in the paper, and that is for troubleshooting truck engines in our workshops. So on this picture here is the Scania XPI fuel injection system, and it's responsible for dosing the correct amount of fuel into the cylinders. And whenever a problem arises on this system, we want to be able to automatically generate a troubleshooting plan that a mechanic in the workshop can use to resolve any problems that occurs on the system. So, for example, we get a warning light with the message the pressure in the fuel ray is unexpectedly low, and this will happen if we measure a different value of the rail pressure that is not expected. And the cause of this could be almost any component that is connected to this fuel rail, so it can be very many. For example, we can have some kind of leakage in the injectors causing the pressure to drop, or we cannot control the pressure because of a fault in the metering valve or the pump, or we just measure it wrong because of a pressure sensor. And to our help, we have actions. We can either replace components to solve the cause of the problem, or we could make measurements to understand what is the cause, and we can also perform other actions to aid us in reaching other actions. The state of the system can be modeled with a set of state variables. Some of these variables we do not know the value of. For example, the health of components. These are partially observable variables. Other variables, however, we do know the value of. For example, whether the engine is on or off. That will always be known. These are fully observable variables. And also we have observation variables representing things that we can observe. For example, the results from tests and measurements that we can do. And what we want is a troubleshooting plan, a conditional plan of actions with step-by-step instructions that can solve our problem no matter what was the cause for it. And this plan we also want to be as cost-efficient as possible with regard to expected time and money for executing the plan. And one way to create these kinds of plans is to model our problem as a partial observable Markov disease process with goals, because we have the goal of resolving our problem and repairing our faults, a goal POMDP. And these are commonly described with a tuple consisting of the states that we can be in, and these states are partially observable, so instead knowledge is described with a belief state in the form of a probability distribution over the states. And we also have an initial belief state from where we start. We have actions that we can do, and these actions have uncertainty in their effects, which is described by a transition function in the form of a conditional probability distribution over the next states that can be reached with an action in a state. Also, we have a cost function describing the non-negative cost of performing actions in different states. Further, in this tuple we have the observations that we can make, and the observation function, which models how knowledge can be gained through the observations, also as a conditional probability distribution. And further, what separates, one of the things that separates goal POMDPs from ordinary POMDPs is that we have goal states. And our objective is to reach one of these goal states with minimal cost, expected cost. And a solution to a goal POMDP is a policy, which is a function that maps belief states to actions in such a way that we can go from the initial belief state to a goal state with finite expected cost. And so here we have the plan from the example. And this plan, well, if we model a problem as a goal POMDP, we can, and then solve it to get our policy, we can get this plan. However, POMDPs are known to be difficult to solve, and our problems is not an exception. However, for our class of problem, there's one thing that we notice here is that we have many actions that are deterministic and only affect fully observable variables. For example, turning on or off the engine, or tilting the cab of the truck. And these actions we call support actions. And if all actions were like these actions, then our problem could be solved more simpler as a stochastic, as a shortest path problem, which is of course simpler. However, we also have the other actions, the one with non-deterministic effects or effects on partially observable variables, or actions that gain information of the belief states. And these actions we say are relevant actions. And what we want to do in our approach is to only focus on the relevant actions when solving the POMDP, and all the necessary support actions that will take us from one relevant action to the next will be solved as a separate problem. And in this way we get macro actions consisting of a sequence of support actions ending with one relevant action. And in this way goal states can be reached in fewer steps, creating a more shallow search space. And how do we do this? Well, we start off with a standard goal POMDP model, and then we transform it into one with macro actions in a pre-compilation steps. And then these transform models can be solved using the standard algorithms that exist for solving POMDPs of this type. And first off, we start off by looking into the model and try to identify which are the fully observable variables in this model. And once we have this, we do a transformation of the action model. I will get to this transformation later on in the presentation, so we'll leave it for now. But once we have done this transformation, we identify which of the actions belong to the class of support actions and which are relevant actions. And for the relevant actions, we then create macro actions for all, using the support actions for all the values of the fully observable variables. And then we can compute new transition observations and cost functions to be used in the transformed POMDP. However, one requirement for this to work is that actions that are applicable must behave in the same way with regard to the partial observable variables, regardless of the values of the fully observable variables. I will explain this with examples, it's easier. For example, we have here the action replace injector. And this action will only be useful if we have tilted the cab, so we have access to the injector. So unless the cab is tilted, if the cab is tilted, then this action will be applicable. That is, it will have can affect the belief state. Also, with this action, when it's in this region of the outcome space of the fully observable variables where it's applicable, it will always have the same effect. It will have the effect that the partial observable variable modeling the health of the injector will always be set to non-faulty, so it will have the same effect in this entire region. However, there are other actions that do not satisfy this requirement. For example, here we have the action of measuring the rail pressure. Well, first of all, the engine must be on for it to be applicable. And once we have the engine on and none of the injectors are plugged, we can plug injectors by removing them and replacing them with a plug. Then we will measure a low pressure in the rail if some of the components that are connected to the rail are faulty. However, if we remove one of the injectors, replace it with a plug to seal this area off, then we will measure low pressure if some component except this injector that we have removed is faulty. So here we get a different behavior with regard to the partially observable variables in different regions of the outcome space of the fully observable variables. And if this was to be the same relevant action, then we have no way of controlling how the resulting macro action, what kind of purpose it will have, because in these different regions, this same action serves different purposes, because we can use it to isolate which injector is faulty. So what we do is, for these types of actions, we create a set of new action where each is given preconditions so that they can only be performed in one disjoint region of the outcome space of the fully observable variables where they behave the same. And this behave the same, it's a soft measure with which we can weigh how many new actions will be created against the model precision of the transformed model. But the minimum requirement is that for all states Si and Sj, if the values of the partial observable variables are the same in Si and Sj, then the probability that the variable, which can either be an observation variable or a state variable in the next state, will have a certain value v if it always gets the value v in state Si, then it must always get the value v in state Sj. Or if it never gets it, it should never get it in Sj. And if it sometimes gets the value in Si, then it must also sometimes get the value in state Sj. For example, if the cab is tilted, then our action replace the injector will always set the health of injector 1 to non-faulty. This partitioning of action may of course cause our total number to increase, and sometimes very much. However, since we only need to consider relevant actions, we also sometimes get fewer actions. And deciding whether it's useful to make this transformation will be a trade-off between search space depth and branching factor. So not all models will be suitable for the transformation. In the paper, we have theoretical results for deciding when our transformation can be applied, so that a goal POMD that is solvable before the transformation, that is, it is possible to find a policy with finite expected cost, will still be solvable after the transformation using the macro action. And we do this by analyzing the graph that we get by using only support actions in the outcome space of the fully observable variables. And especially we look at the strongly connected components of this graph. And if either one of the results that we have is that if either each action is applicable in only a single strongly connected component, or all actions are applicable in all strongly connected components, then this solvability property will be preserved. And what this means is that if we have a path to a goal state using relevant actions and support actions in the original model, then if we remove all the support actions and replace them with other support actions that we get from generating the macro actions with which we don't have control over, then we will still be able to find all these support actions. This is described further in the paper, and we also have proofs there. Also, we have done some experiments on various gold POMDs where we have seen that our method is effective. And the first example here is a domain that we call avalanche domain. And here we have a UAV that is navigating a grid in search of persons hidden beneath the snow. And to its aid, it has a long-range directional sensor. And all the movement of the UAV and the location of it is deterministic and fully observable. However, the locations of the persons is partially observable, and the sensor is noisy. So when we perform our transformation, what we get is that all the movement actions will become support actions, and the macro actions will take us between relevant parts in the grid where interesting measurements can be made. And here we have done the transformation, and we applied the solver heuristic search value iteration 2, and we measured the quality of the policy at different times, and we see here that we get a great improvement on this model. And also noted here we have the compilation time, which is only pre-compilation time of creating the transformation, which is only a few seconds. Second example is the gold rock sample. It's adaptation of the rock sample domain, which is for normal discount POMD, and here we adapted it just slightly for gold POMD. And again, movement is deterministic, and we have fully observable location. And for the results, we still see an improvement. But if we note here for the larger instance here that we show here, we will actually get lower expected cost in the untransformed model. And this is because our transformation may cause us to get lose optimal solutions. So in this case, we actually have faster convergence, but the optimal value expected cost in the transformed model is slightly higher. The last example I will show is from the domain that we are interested in for troubleshooting trucks, and here is a model of a truck braking system. And still we get the same kinds of results, that the transformation is useful in this case. And here we show two of the instances that we used in the paper, the smallest and largest ones, state-wise. And we have also in the paper, we have used another algorithm also, forward search value iteration. And we get similar results. So for the conclusion, what we have here is a new method for exploiting deterministic actions and fully observable variables in gold POMDs. And this transformation is general. It works for almost all factored gold POMDs. And the transformed POMD can then be solved using a standard algorithm. And if applied on a suitable problem, we can improve the convergence time of the solver significantly. And that's all I had to say now. Questions, please.